Hello everyone, welcome to our new tutorial video for the continuation of solving problems of thermodynamics question from MIT, together with me Inusarabi Isa, popularly known as Bodmas. So let's start with reading the question. As part of a heat treating operation, a still fat with a mass of 100 kg is to be quenched from a temperature of 1000 degrees C to a temperature of 50 degrees C by plunging the fat into a water bath enclosed in an adiabatic chamber. The initial temperature of the water bath is 20 degrees C. The water bath and the still fat can be modeled as pure thermal system with specific capacity of water equal to 4.187 kJ per kilogram per Kelvin, and the specific capacity of steel is equal to 0.473 kJ per kilogram per Kelvin. Roman 1. Describes the model suitable to determine the amount of water necessary to perform this part of heat treating process. Roman 2. What is the necessary amount of water? Roman 3. Calculate the heat transfer for the system consisting of the still fat and the water. Roman 4. Calculate the heat transfer for the still fat. Roman 5. Calculate the heat transfer for the water. Roman 6. Calculate the entropy change for the still fat. Roman 7. Calculate the entropy change for the water. Roman 8. Calculate the entropy change for the system consisting of the still fat and the water. Roman 9. Calculate the entropy transfer for the system consisting of the still fat and the water. Roman 10. Calculate the entropy generated for the system consisting of the still fat and the water. Roman 11. Was this part of the heating operation reversible or irreversible? So let's start with some solution as usual. Now Roman 1, we ask to describe the model. So our task is the model suitable to determine the amount of water. So now we follow the normal procedure, as simple as we are doing. That is a step in solving problem with thermodynamics. So we describe our system. So our system, we consider the still and water to be our system. So still and the water are our system. So now we are to describe the states. So initial we have initial and final state. So now the initial temperature, that is T1 of still, is equal to 1000 degrees C, and then the final temperature, that's the equilibrium temperature they reach, is 50 degrees C from the question. And also the initial temperature of water is 20 degrees C, and the final temperature of water, that the equilibrium temperature that both still and water reach, is 50 degrees C. So then we have interactions. So taking still part and water part as a system, then and placed in an adiabatic chamber, meaning there will be no heat transfer for this system. So heat transfer is 0, and there is no work. It's obvious, since the system is stationary, it's not moving, it's not doing any work to the surrounding or receiving work from the surrounding. So the interaction, the work is also 0. So now we apply the first law of thermodynamics. So apply the first law. So we apply the first law. So the change in energy of the system is equal to the heat minus the work net. So the heat is 0 and also the work net is 0. So this implies that the total energy, so the change in energy of the system, that is the still part or the water, plus the change in energy of still, that is our system. So this means that the change in energy of the water is equal to the change in energy of the still. So we substitute the values. So now the change in energy of water is equal to the change in potential energy plus the change in kinetic energy plus the change in internal energy. So the system is stationary by assumption, so potential energy and kinetic energy are all 0, and also the change in energy of still is equal to the change in potential energy plus the change in kinetic energy plus the change in internal energy of water of still. So this is also 0, this is also 0. So this means that so we apply the formula, that is, this is the mass of water times specific capacity of water into change in temperature of water minus the change in minus T1. So it's equal to minus the mass of steel, specific capacity of steel, into theta 2 of steel minus theta 1 of steel. So mass of water, specific capacity of water, theta 2 of water minus theta 1 of water is equal to mass of steel, specific capacity of steel, into theta 1 of steel minus theta 2 of steel. So I multiply minus the bracket. Therefore, since the model asks us to describe the process to which the mass of water can be analyzed or find, so we make the mass of water to be the subject of the formula. So mass of water is equal to the mass of steel, specific capacity of steel, into theta 1 of steel minus theta 2 of steel divided by the specific capacity of water into theta 2 of water minus theta 1 of water. So this is a model. Actually, we substitute and solve for. So that is a model. That's a suitable model we can use to determine the amount of water. So then Roman 2, we asked to determine the amount of water. So we use the model, or we apply So what is a model? So the model is mass of water is equal to the mass of steel, specific capacity of steel, into temperature of 1 of steel minus temperature 2 of steel, divided by the specific capacity of water into temperature 2 of water minus temperature 1 of water. So we substitute the given values. So what is the mass of steel? The mass of steel is 100 kilogram times specific capacity, which is 0.473 into the change in temperature, that is 1000 minus 50, divided by the specific capacity of water, which is 4.187, then theta 2 minus theta 1, which is 20. So we substitute the given value and solve. We got mass of water to be equal to 357.73 kilogram. So that is the mass of water required. Then Roman 3, in Roman 3 they ask us to take steel and water as a system. So now system, and find the work, the heat transfer. The system is steel and water. So for this, what is the interaction? The interactions, they are sealed in an adiabatic chamber. So interaction work is 0. Heat is 0, and also work is 0. So therefore heat transfer is 0 joule. Had it been, if it is still only as a, taken as a system, then there is heat transfer actually, or water part. But if we take them as a system, then there will be no heat transfer according to the interaction we observe. Then Roman 4. So Roman 4 system. We asked to take the steel part only as a system. So steel part as our system. So now what is the interaction? We have already described the state, so we don't have to be mention them always. So what is the interactions? So the interactions. So now the heat is not equal to 0, and there will be no work transfer. So for this we apply the first law of thermodynamics. the change in energy of the system, that is still, is equal to the work, the heat minus the work. So the work is 0. So this means that the energy, the heat transfer is equal to the change in energy of the steel, which is the change in internal energy of the steel, neglecting the kinetic energy and potential energy. So this is equal to the mass of the steel, specific capacity of steel, temperature 2 of the steel minus temperature 1. So we substitute the given value and solve. This is 100 kilogram times specific heat capacity, which is 0.473 into 50 minus 1000. So substituting, and we got heat is equal to minus 4.935 kilojoule. So the negative sign indicates that the heat is lost. This means that the heat is lost from the steel to water, which is true because steel is at high temperature than water. So therefore steel lost heat to the surrounding if it consider at the system. So row 5. So row 5 we take water at the system as instructed. So our system is now water. So what is our interactions? So our interactions, the heat is not equal to 0, but the work is 0. The work is 0. So we apply first law of thermodynamics, and the energy of the system, that is water, is equal to the heat transfer minus the work transfer. So the work is 0. So heat transfer is equal to the change in energy of water, which is equal to the change in internal energy of water by neglecting kinetic energy and potential energy. This is equal to the mass of water we obtain into specific capacity of water into change in temperature theta 2 of water minus the theta 1 of water. So this is equal to the mass of water we obtain, that is approximately 357.73 times specific capacity of water, which is 4.1H7 into 50 minus 20. So by doing this we got 4.935 kilojoule, which is the same as the amount but opposite amount of water, the heat transfer gotten by taking still only at the system. So alternatively we can apply the Zero's law of thermodynamics by Zero's law. So since the water and steel are only the component, so the heat transfer by steel plus the heat transfer by water is equal to 0. The heat transfer by water is equal to minus the heat transfer by steel. So the heat transfer by water will going to be minus into minus 4.935. So therefore the heat transfer by water is going to be equal to 0.0444935 kilojoule, as we got by using the first law of thermodynamics. So it's also valid to use a zeroth law of thermodynamics. Then we got Roman 6. So Roman 6, we ask to find the entropy change of water. So water is a liquid, therefore the entropy change of water will going to be equal to the mass of water, specific capacity of water, then the natural logarithms of theta 2 to theta 1 of water. So we substitute our value, which is equal to 357.73 times 4.187 ln theta 2, but the theta is going to be, or we can say must be in Kelvin, not Celsius. So the temperature must be in Kelvin. So we convert them, that is 50 plus 273 all over 20 plus 273. Actually it's wrong to use temperature in Celsius. So by substituting, we got the entropy change of water to be equal to 146 kilojoule per Kelvin. So the entropy change of water is equal to this. Then Roman 8, we ask to find the entropy change of steel. This is Roman 6, this is Roman 7. So it's Roman 7. So in Roman 7 we ask to find the entropy change of steel. So steel is a solid, so we apply the some formulas. So mass of steel, specific capacity of steel, into temperature 2 of steel all over the temperature 1 of steel. So this is equal to the mass of steel. The mass of steel, which is 100 times specific capacity, which is 0.473 natural logarithm of temperature 2, which is 50 plus 273 all over the temperature 1, which is 1000 plus 273. So by substituting the value, we get the change in entropy of the steel is equal to minus 64.87 kilojoule per Kelvin. Then Roman 8, we ask to find the entropy change for the system consisting steel fat and the water fat to steel and water. This will going to be the summation of the change in entropy of steel and water. So it's going to be the entropy change of steel plus the entropy change of water. So this is equal to minus 64.87 plus 146, which is equal to 81.13 kilojoule per Kelvin. So the entropy change of steel and water fat is equal to 81.13 kilojoule per Kelvin. So then Roman 10, we asked to find the entropy generated for the still fat and the water fat. So by taking the still and water as the system, then and we apply the second law of thermodynamics. So the entropy change of still and water is equal to the entropy transfer plus the entropy generated. So it's equal to the entropy transfer, which is integral from 1 to 2 over the constant temperature plus the entropy generation. So still fat and water fat are considered to be isolated or adiabatic systems because there will be no heat transfer. So this is 0. Therefore, the entropy generated is equal to the change in entropy of still and water. So from Roman 9, this is equal to 81.13 kilojoule per Kelvin. So Roman 11, we ask to determine whether the process is reversible or irreversible. So we have 3 conditions. So let's describe the condition and then we conclude. So condition 1, the entropy, if the entropy generated is less than 0, the process is reversible. The process is reversible. No, sorry,